So our second speaker tonight is Hamidreza Ermagan, a Ph.D. student in the Department of Mining and Materials Engineering, working under the supervision of Professor Agus Sasmito, and is co-supervised by Professor Leila Amiri from the Department of Mechanical Engineering at L'Université de Sherbrooke. Tonight, Hamidreza is going to talk to us about an old method of energy storage that can move us towards a greener future. Hamidreza.
Renewables are not always available when needed, and they're not always needed when available. So here's the thing that we should work out. We need to find a way to address this mismatch between energy supply and demand. And for that, we can store energy when we have access to it to later on use it when we don't. But the current energy storage trend is not sustainable, as it mainly relies on lithium-ion batteries, and we are already facing a shortage in critical minerals. Well, although many ongoing research is being done to improve battery sustainability as well as efficiency, but as of now, most batteries are not sustainable, and I'll tell you why. Well, batteries are relatively expensive because of two main reasons. First, the raw materials that are used in them are expensive because they're highly in demand in various industries. Second, if we want to use these materials inside these batteries, we need them in their purest form, which means additional processing, which translates to additional cost. Most batteries are also not environmentally friendly, and there are, again, two reasons for that. First, the whole mining and processing of these materials can harm our environment. Second, the fact that we need to make these batteries, like when we are done with these batteries and when we want to dispose them, the toxic chemicals that are inside them can contaminate our water supplies as well as soil and our whole ecosystem. Speaking about their lifespan, they are also not that long lasting, and you don't need me to tell you why. You have your smartphone batteries to do the talking. What if I told you there is an alternative sustainable for that, which is much cheaper, around 1/10 in price, which is much more environmentally friendly, and which is basically much durable, around 3 times longer? Well, to give you a clue about that, let us travel back in time to see how our ancestors used to store energy. Well, back then, people would cook completely different than the way we do today. So what they would do was to dig a hole and fill it with stones. Then these stones would absorb the heat of the sun during daytime, and this heat was gradually released overnight to cook people's food. Fast forward to around 500 years ago, which was supposedly a very cold time in our history, there was this building that would offer the residents an extremely warm all day long. Well, in this building, what was done, that tall windows were placed that would allow the sunlight to be absorbed by a huge spine wall. This spine wall would then gradually release the heat overnight to keep all the residents warm. Well, as you might have already guessed it, we are going to store energy inside rocks. Well, rocks do exceptionally well at withstanding really high temperatures. And that is really important for us, because we are not only interested in storing heat as heat, we want to transform it to electricity. And for that, we need to be working with really high temperatures. Also, storing energy inside rocks can not only be used for short-term applications, like daily storages, but they can also be used for longer-term applications, say for seasonal storage. Well, let us take a look at how our thermal energy storage system, which is based on rock, works. Well, the whole concept of storing energy inside rocks is pretty straightforward. All we have to do is to send hot air through the initially cold packed bed of rocks. By doing so, we are increasing the temperature of the rocks as well as the energy contained within the systems. So then, when our system is fully charged, we reach the point of standby, in which we can store energy for as much as we want, provided that this system is well insulated. And this gives us the energy storage that we want. Later on, whenever we want to use it, all we have to do is to send cool air to extract the heat from these now hot rocks. As you can see, the energy within the rocks would decrease, and all this energy would be transferred to our air. And this hot air can be later be put in really good use that we'll get into shortly. Well, now that we are familiar with how this system works, let us see how sustainable they are. Well, the sustainability of our whole system really comes down to how this air is heated and how it is delivered to the system. And for that, what we plan to do is to use renewables. So basically what we'll do is to use the clean electricity produced from solar panels or wind turbine to run an electric heater. Then this electric heater would hit the air and would be sent to our packed bed of rocks. And how this heat would be stored later in the discharging cycle is to just be used to run a gas turbine, in which the hot gas, which is now full of energy, can rotate the blades of a gas turbine to create electricity for us. Well, this is an overview of the proposed system and how the packed bed of rock can act as our missing link for energy storage. Well, as you can see, there are many components in our system. We have the renewables component, we have our fan and electric heater, of course we have our packed bed of rock, which acts as the energy storage, and then we have our electricity generation component. So in my initial phase of the research, what we're interested is to see how this packed bed of rock works. So for that, we can do experimental setup. So that's actually what we have already done. With the help of our colleagues at University of Sherbrooke, we have an experimental setup to see how the heat exchange between the air and rocks are happening. As you can see, this is our packed bed of rocks. We have a heat gun to provide hot air for us. The system is insulated so that we can create the storage that we want. And also there are thermocouples located at different axial points to measure the temperature for us. However, we are losing out on a powerful tools, which are numerical simulations. So I'll tell you why they are so beneficial for us. Well, first of all, we are dealing with really high temperatures, and it's much safer to do the testing with numerical methods compared to the experimentals. And also, we have this opportunity to test different storage materials. This numerical simulation can give us a cost-effective method to test different storage materials as well as heat transfer fluids. So for instance, what is the right type of rock to be used in our storage system? Is it limestone or is it sandstone? Or should we use magnetite? And also, why are we even sending air? Why not thermal oils or molten salt? So there are many options for us that numerical methods will provide a cost-effective method to predict them. Now that we know how powerful numerical methods are, let us consider two common approaches to predict the temperature in this packed bed of rocks. So we can either use macroscale or microscale simulation. So in macroscale simulation, we consider the whole packed bed of rock and only include the overall effect of these rocks. We do not take them individually. And this is the results that we get. As you can see, as the air is moving through this packed bed of rock, it is heating our system, and this is what we actually want. This is what we call macroscale simulation. But in microscale simulation, what we're interested is to include the effect of the presence of each and every rock. And this is the result that we get if we do the microscale simulation. Well, now that we know these two numerical methods are available at our disposal, let us compare them and see which one gives a better prediction of the overall performance of the system. So for doing that, we have compared these numerical solutions with what experimental data gives us. So for that, we have considered the charging cycle. So imagine that we are sending air at relatively high temperature, a temperature of 700 Kelvin, and we have our rock at the room temperature. So after 1 hour into the charging, this is the experimental result that we get. As you can see, the initial part of the packed bed is already heated up. After 4 hours of sending the air, and after 4 hours into the charging cycle, this is the results that we get. As you can see, almost half of the packed bed temperature has increased. And after 7 hours, almost the majority of the packed bed is heated. So this is our experimental data. Let us compare the two numerical methods that I mentioned earlier and see how they would predict the temperature profile along the packed bed of rock. Well, this is the results that we get when using macro-scale simulations. As you can see, although the general trend is being predicted, but the experimental data and numerical results vary significantly. However, let us see what happens if we take the micro-scale approach. This is the results that we get. As you can see, the results almost perfectly agree, meaning that we have a powerful numerical simulation. With this numerical technique that is really powerful in predicting the temperature along the packed bed, we are confident in following the many objectives that we have in this research project. One of the objectives that we are following is to see how the rock sizes would predict the overall performance of the system. So, if we decrease the size of the particles, we would need a much larger fan. And that is because it is much more difficult to send the air through the now more packed bed of rocks. However, it can fasten the charging and discharging cycle and also produces more electricity for us, which are both good things. However, if we go with larger particles, intuitively, we'll need a much smaller fan, which is a good thing. However, it will prolong the charging and discharging time as well as the electricity that is produced, meaning that there is a trade-off for the optimal size of the rocks. And since we now have the right numerical framework, we can answer this question much more easily. Well, overall, although renewables offer a clean source of power to us, but they are of no good use if we cannot accurately predict what's happening. And what I aspire to do in this research project is not only to make the source of our energy clean, but to make the whole chain of the energy usage clean, which is not possible unless we master the art of thermal energy storage. Thank you.